Hello everyone, we're beginning chapter 23 today, and just as a quick recap, in the previous videos relating to chapter 22 we focused quite a bit on the derivations of electric fields for different distributions of charge, and understandably those were not the easiest of derivations. Mainly because we had to spend a lot of time analyzing how all of that charge was distributed in the system so that we could set up the proper integration. But we did see that there was a little bit of relationship to the geometry of the system. So given the different ways that we would spread the charge out in the system, we could take advantage of different symmetries. And so in chapter 23, which focuses on something called Gauss's Law, we're going to see if we can take a greater advantage of the geometric approach as opposed to the calculus approach. That's not to say there won't be any calculus, it'll just be an easier setup. And what Gauss did was he kind of picked up on the patterns of what was occurring every time they would find the expression for an electric field, and he put that together in this statement called Gauss's Law. And we'll go ahead and read through this and then try to make sense of it later on in this video. But Gauss's Law will take the electric field that passes through a closed Gaussian surface, and we'll define what that is here in a few moments, and then relate that to the charge that is enclosed by that surface. So like any of the previous derivations, we're going to have some amount of charge that has been distributed in some fashion. The easiest of any of those distributions is just going to be a single point charge, so we'll start there. And as we already know, this point charge is producing electric field lines. For positive charges, those field lines will travel outward in all directions, producing a ever-expanding sphere of electric fields, and that electric field has a magnitude of Q over R squared. So this is something that we already know. Well, Gauss said, since we have that charge, and since that charge is producing all of these electric fields, let's contain it. Let's put a container around this charge, and then we'll look at how those electric fields pass through the surface of that container. So we'll do that, but the way that Gauss's law works, so we're actually going to take a moment and rewrite this verbal expression into a math expression. So Gauss said that we can take the electric field that passes through a closed Gaussian surface and relate it to the enclosed charge. So right here we have what we're going to call the enclosed charge, and we're going to relate it to a term that we call electric flux. So this capital Phi here, this stands for electric flux. Electric flux. And what electric flux is it takes the electric field and pairs it together with the cross-sectional area that field passes through. And so a little side example to help us understand this better would be like a window, and if you open the window and you want to get some air to blow through the window, the window itself has a cross-sectional area that we can call A, and that cross-sectional area actually points in a direction. So if you think about the window pane and the direction that that window pane faces, that window pane is going to face outward, perpendicular to the surface of the window itself. And so this is kind of an interesting way of expressing area. We can actually express area as a vector. And you could do the same thing with a table if you wanted. If you look at a table and you ask yourself, well, here's the surface of the table, which way does the surface point? It points up. So any surface we can assign an area vector to, and that area vector will always point perpendicular to the given surface. Well, so why is that important when it comes to things like a window or wanting to get air to pass through it? If you open the window and it's a windy day outside, well, which way is the wind blowing? Is it blowing directly into the window? If so, the velocity of the air would carry the air through the window, and you'd get a very high flow rate of air. But if the wind was blowing perpendicular to the window, well, you're not going to get much airflow through that window. And so there becomes a noticeable relationship between the angle that our air flows with respect to the direction that the area vector is flowing. We're obviously going to get more airflow through the window if we have the air flowing in the same direction as what the area vector is pointing. And so we can take the same idea of electric flux and we can just modify it for the flux of the air that passes through the window. And what I've done here is I've introduced a dot product because I need something that will not only help to relate the two terms together. Obviously, if I have a larger window, I can get more airflow through, and obviously if the wind is blowing faster, I can get more airflow through. But then I have to consider at what angle are these two in relationship to each other. If I have the air blowing parallel to the window, then that angle relationship is 0 degrees. And this is where I would see the maximum amount of airflow occur. So what trig function is going to maximize at 0 degrees? Versus if I had airflow flowing perpendicular to the cross-sectional area, that's a 90-degree relationship, and there would be no airflow through the window. So I also need a trig function that is going to minimize at 90 degrees, and together the only way to get that to work is to use cosine. And that's what dot product utilizes. And so not only will we need to use a dot product for the airflow analogy, but we would also need to use a dot product for the electric flux analogy. So here we have air flux. Up there would be electric flux. Now this air flux, we're not going to use it any further. This was just here as a more basic example of how the math works and why the math works. And so going back to Gauss's law says, okay, the electric field that passes through the Gaussian surface. Okay, so we're getting closer. We're talking about the electric field passing through a given surface area. So putting all that together, what we're really talking about is electric flux. And that's what we have there. And we're going to be relating that to the charge that is enclosed by that surface area. The one extra piece that we have in Gauss's law here is epsilon naught, and that is that permittivity value that describes how all of our electric phenomenon are going to behave inside of a vacuum. So we need that there, but this is also kind of a precursor as to how we're going to prove where the value of K is coming from. Now we'll take this and we'll expand it a little bit to include the actual flux of a material. Except that anytime you have a surface area, typically that surface area is made up of a two-dimensional construct. So one way to think of it is if you had a block, each side of that block has a given surface area to it, but if I were to place a charge inside of that block, those electric fields are going to be passing through all of the different faces of that block. And we need to know how do the electric fields pass through each of those faces individually, and then since the product of a dot product is a scalar, we can actually add up the individual flux from each face of the container that we are using. So adding things up, in this case, since each face of the cube is predefined, we would just add up the individual flux values from each face. But not all shapes are going to be as simple to work with. When it comes to the individual charge over here, all of our electric field lines are extending outward along the radial direction. And so it would be very convenient if I could use something like a sphere as the container. And so the surface of that sphere has now become the surface of my Gaussian surface, or what I would like to call my Gaussian container, for lack of a better term. But this is going to be the Gaussian surface that we're talking about. It looks too much like a theta. It's supposed to be a G. This is our Gaussian surface. The area of a sphere, well, we can look that up. That's not a big deal. Area of a sphere is 4 pi r squared. But what direction does the area of the sphere point? With the cube, it's not that big of a deal. We just look at the direction that each face is pointing and we call it good. But for a sphere, well, there's a little piece of the sphere up here at the top that points up. There's a little piece of the sphere down here that points down. There's a piece over here that points to the right, to the left, and well, I can go all the way around the sphere, and anywhere I look, I'm going to have these little infinitesimal surface areas that are pointing away from the surface of the sphere. If I want to get the total flux through the surface of this sphere, well, I'm going to have quite a time going around trying to individually add up all of these individual pieces as a summation. And so instead, what we will do is we will integrate about the surface of our container. So our expression right here for the electric flux in any given system, we are going to write that in the most general case possible, which is an integration of the electric fields as they pass through the surface area of our container. And so that ensures that we're adding up all of the electric fields that pass through all portions of the surface area. And just to help remind us that these surface areas are going to be three-dimensional, we're going to put a little circle around the center of the integral sign, and this tells us and whoever's looking at our work that this is a closed surface integral. So we are integrating about the surface of whatever shape that we're using. So in our case, it is the sphere. And now we're ready to get started. We're going to take that individual charge of Q. We're going to place it inside of this imaginary spherical shell, which will act as our Gaussian surface. And then we'll look at all of the electric field lines that are being produced. And as those electric field lines pass through the Gaussian surface, we want to take a look at each individual piece of surface area that those electric field lines are passing through. So right there's an infinitesimal little kind of like a tongue twister here. There is an infinitesimal amount of surface area that electric field passes through. And so we're going to call that dA. So infinitesimal surface area. But every other electric field is also passing through its own infinitesimal surface area. And so we're going to go all the way around this sphere, adding up the contributions of electric field and surface area. But here's the really cool thing. No matter what portion I look at, whether it's this portion or that portion or the portion up top, the electric field vector at that particular location is running parallel to the infinitesimal surface area vector. Just like here, both of those vectors are pointing in the same direction. They're running parallel. Up here, they're running parallel. And so we can take the dot product that is inside of our closed integral, and we can say there's a cosine relationship between those two vectors, but no matter where I look, those angle relationships are always 0, and cosine of 0 evaluates to a 1. And so now all that's left is the integration. We actually lose the vector hats now because we've evaluated the dot product, and the outcome of a dot product is a scalar. Now this is not something that we just get to get rid of every time we use Gauss's law. We actually have to take the time and look at the relationship between our electric fields and our surface areas. And we'll see additional examples of how we're going to use Gauss's law in the future. But for right now, this is what we have for the sphere. So we'll come down here and collect what we have so far. Epsilon naught, closed integral, E dA. All right. Well, that enclosed charge value, how much charge do we have enclosed? Well, let's take this charge and we'll give it a value. We'll call it Q. So I have enclosed some generic amount of charge Q. And that relates to the electric flux that is passing through all the surfaces of this container. And so now what I need to do is I need to figure out what my next step is going to be. Keep in mind, we already know what our answer should be. We already know that the electric field for a point charge should be kq over r squared. And the whole point of this expression is that no matter where I go on the surface of this sphere, I'm always the same radial distance away from the charge. As such, no matter where I go on the surface of the sphere, I have the same magnitude of electric field. That means the electric field is uniform at all points on the surface of the sphere. If we take that idea and apply it to the integration that we're about to do, well, now we're assuming that the electric field should be uniform at all points on the surface of this sphere. If the electric field is a uniform value, then it can be brought outside of the integral. And now the last thing that we have to do is we have to integrate about the surface of a sphere. Well, no problem, because we already looked that up. We can Google that, or we can go into the appendix of our book, but the surface area of a sphere of radius r is just 4 pi r squared. So even though we had what looked like it was going to be kind of an intimidating three-dimensional integration, we were basically able to bypass all of that. And the integration's done. We have an algebraic expression sitting in front of us. All that's left is to rearrange and solve for the electric field. If we do that, we already have Q on the one side. We would have to divide out by everything else, and well, look what happens. We get 4 pi epsilon, which is k, and we have r squared. So we have exactly what we've been using the whole time. We have kq over r squared. And you might be saying to yourself, well, yeah, we already knew that. Why did we have to go through a different process to get the same equation? Well, two reasons. First of all, it's always good if you can reproduce an expression using a different approach. But this approach specifically shows us where the value of k originates from. So this is why we're going to be using 1 over 4 pi epsilon from now on. And the epsilon naught value, we can plug that in as needed. But remember, anytime you see this combination anywhere in your work, you can still plug it in as the K value that we've been using all along. Okay, well that's for a single point charge. What other kinds of collection of charge are out there? And how could we apply Gauss's law to those? Well, the next combination of charge that we attempted, at least back in the previous chapter, was a line of charge. And you're probably thinking, oh, I hate this one. And I agree, this was by far the worst of all of those calculus derivations that we did for fields. And you might be thinking, you know, we've already got the expression for it. Let's just use it. But we want to see if Gauss's law works for all of these case scenarios. When we set up the line of charge, the first thing that our author did was suggest that we allow this line of charge to extend out to infinity. And that way, whatever point out in space that we use to try and measure the electric field will automatically be the midpoint of the line. And we used z to designate the distance from the line out to that point. But if the line is infinitely long, that means that any point that I choose should be the midpoint. And since we've already solved for the electric field at this point, then we should expect to see the exact same electric field magnitude at all of these other points. What made Gauss's law work so well for the sphere was that we were able to argue the fact that the electric field should be uniform at all points on the surface of our Gaussian surface. And that meant that we could pull that electric field expression outside of the integration, and then we were able to solve for the field magnitude. So we want to see if we can reproduce that trick here. It looks like everywhere along this line we're going to see the same magnitude of electric field. So everywhere there we have a uniform electric field magnitude. Every one of those points is a distance of z from the line of charge. Are there any other points out in space that are also a distance of z from that line? And the answer is yes. There's also a distance of z that we can drop below the line. But we also have to think in 3 dimensions. That z could be used as a radial vector that we could then rotate around that line of charge and sweep out the shape of a cylinder. And it is now the line of charge that acts as the central axis of that cylinder. And we are expecting to see uniform electric field passing through every single point along the surface of that cylinder. And a bonus to this is that we've automatically enclosed the charge of that line. And that's one of the requirements of Gauss's law, is that we have some kind of enclosed structure that the electric field lines can pass through. All right, next let's take a look at the electric field lines. If you remember our evil twin scenario, these charges are going to send their electric field lines up, but because of the symmetry of the system, only the vertical components of the electric field are actually going to survive. And so all along the length of this cylinder, we're going to see electric field lines passing through in a direction that is, what other color could I use? I'll use orange. All those electric field lines, oops, call those E, E, E. All those electric field lines are pointing in a direction that is parallel to the infinitesimal surface area that they pass through. So just like the sphere, we have electric field lines that are running parallel to the area vectors. And this will also be true as we go all the way around the cylinder. Those electric field lines are going to point radially outward. And that means that every time we look at the pairing of electric field and surface area, there's going to be another cosine 0, or that cosine relationship will go to 1. So now we reduce our dot product down to just EDA. So we've lost the vector notation. Just like before, we're arguing the fact that the electric field should be of a uniform value at all points on the surface of our container. So we bring E outside of the integral. And the last thing that we have to do is we have to figure out what is the surface area of the cylinder that we're passing through. Now here's where things can get a bit tricky. Last time the author said, let the line go to infinity, it'll make your job easier. And to an extent that was true, but I can't integrate the surface of an infinitely long cylinder. I'm going to get infinity. And we know from our previous derivation that we did not get infinity for the electric field. So what I'm going to do is I'm going to backtrack here. We'll take this infinitely long cylinder and we'll pare it down to something that is finite in length. So we can give this line a length of L. But that means as we get closer and closer to one of the edges of the line, we're not going to see as much of a uniform electric field. So we'll focus our attentions just at the midpoint, which is basically where we focused our attentions using the calculus approach from before. Well, I have my electric field. I'm sort of hand wavy, expecting that this would be uniform at all points along the surface. I just need to know now what the surface is that the electric field is passing through. Because the cylinder is now finite in length, I can produce a finite surface area. You'll notice that the electric field line is only passing through this drum portion of the cylinder. It does not actually pass through the end caps. And if I don't have any electric field passing through the end caps, then there's no electric flux for those end caps. So I don't need to worry about the surface area of the end caps, which technically would be pi r squared. In this case, r is equal to the z value. But since we're not passing through those, we don't have to worry about them. We do need to worry about the surface area of this drum portion here. And a cylinder, if you were to take a cylinder and cut it, so if you were to grab a pair of scissors and start cutting, and then unfold it, you would get the shape of a rectangle, and that rectangle would have dimensions of L and 2 pi r, which is the circumference of the cylinder. Since we're using z instead of r, this would be 2 pi z. But we want the area. Well, the area of a rectangle is length times width, and we've got the length. The width is the circumference that we just used. So there's the area of the drum portion of the cylinder that we need to pass through, and that is going to go into our integral. The charge of the line. This is another reason why we wanted to use a finite line, is that for an infinitely long line of charge, we would have infinite charge, and we can't do that. But for a finite line, we can have a finite amount of charge. So we'll again use generic Q. We need to import the area, 2 pi ZL, and we're done. We have our calculus completed. We can now rearrange to solve for the electric field, and we have Q over 2 pi epsilon ZL. Now, if you remember back to that derivation that we did with the line of charge, one of the things that we had to know to set up that pretty intense calculus derivation was how all of this charge was distributed about the line. And for that, we introduced the idea of lambda, which was charge per unit length. Well, look what showed up in our expression here. We have literally lambda. We have lambda over 2 pi epsilon z, and now we have the electric field. And we were able to reproduce that really without too much hassle. Starting with Gauss's law, and then working our way through basically mapping how the electric field would pass through a given container, we were able to reproduce the electric field expression without having to rely so heavily on all of the calculus and the fact that there were I think there were like 4 different variables in this system when we tried to do this with the calculus approach. But here, just letting the geometry basically do its thing, and the fact that we are working with a symmetric system really cuts down on the amount of work that we have to do in producing these expressions. Now, again, once we get to the end result, that's what we are expected to work with. But the reason that we're going through and we're seeing how Gauss's law works is because there might be some future distributions of charge that we haven't considered yet. And we now have a choice of using some very complex calculus and integration to set up the math to solve for the electric fields, or we can use Gauss's law to set up the math and solve for the electric field. And typically Gauss's law by far is going to be the easier approach. The only time Gauss's law doesn't work out that well is if we find ourselves with an asymmetric system of charge. Gauss's law really takes advantage of that idea of symmetry and really helps us out. But if we don't have a symmetric system, we almost exclusively have to rely on the calculus to tell us how those integrals are going to turn out. But since we've already gone through and we've seen enough examples of that calculus, we want to devote more of our time to the easier approach. Alright, let's see what we want to do next. The next thing we'll do is we'll go back and reproduce yet another expression that we already know, but using Gauss's law. Let's consider a charged sphere. And there are a couple of different combinations that we can have when considering a charged sphere. So we can have a sphere that's made of a conducting material or an insulating material. We could have a sphere that is solid, or a shell of a certain thickness. And so of these four different possible combinations, we want to see how Gauss's law would work in expressing the electric field of a sphere. Thinking back to the previous chapter, we said that as long as the charge is uniformly distributed about our shape, we can use an idea similar to center of mass and collapse all of the charge down to a single point, and then use that charge as a point charge. In other words, we can express the sphere as a point charge. But this is only going to work if we are somewhere outside of the construct of the sphere. So as long as I'm still a distance of r away from the center of the sphere, I can treat the sphere like a point charge. That's a very useful conclusion. And so Q over r squared. So either way, if it's a uniformly charged sphere or just a point charge, we can use the point charge expression for both of them. Well, that brings us to the four different case scenarios. Let's consider these four different case scenarios here and how Gauss's law would work. So we'll clean this up a little bit. So that's our end result. We want to see if we can reproduce it using Gauss's law. That's our goal for this next exercise. So we have our sphere of radius r, and we'll start with case scenario 1, where we have a solid conducting sphere. Because it is a conductor, the charge will automatically distribute itself about the surface of the sphere uniformly. And so we automatically have our uniform charge distribution. And I would like to know what is the magnitude of the electric field at a distance of r. So big R is the radius of the physical solid sphere. Little r is going to be the position where I want to measure the electric field. But it shouldn't matter where I measure r. There are a lot of different points out in space that are a distance of r from the center of the sphere. And it makes sense that every one of those points should experience the same magnitude of electric field. I know I didn't draw all of those correctly, but we'll say that every point on this sphere is a distance of r, little r, from the center of the system. So no matter where I look, I should expect the same electric field magnitude. And if spheres are going to act like point charges, we could then argue that electric field lines that pass through the surface, for instance, at the very bottom of the sphere, I should see an electric field line that points directly down. Now, why is that? We have all of these point charges. Every one of them is going to send their electric field lines down to that surface, but regardless of the evil twin pairing that I get, what happens when those field lines intersect at the surface? Well, I lose all of the components that are horizontal, and I only keep the ones that are vertical. It's that symmetry idea resurfacing, and it's showing us that only the electric field components that run perpendicular to the surface of our container are actually going to survive and pass through. So I have a infinitesimal amount of surface right here at the bottom of the sphere, and all of the charges on that charged sphere, they add up at this point. Oops, did not want to do that. Can we go back? There we go. All those charges are going to be sending their field lines down to that point, but all of the horizontal components are going to cancel out, leaving us with just that vertical component. Well, what about other locations on the surface of our Gaussian surface? Because that's really what this is becoming now. Let's see. Let's pick this point over here to the far left. All these charges are going to be sending their electric field lines over, but now it's not the horizontal components that are going to cancel, it's the vertical components. Some of the components are pointing up and down, but due to the symmetry they're all going to cancel out, and I'll be left with electric field lines that point just to the left. This is very similar to what we saw with the individual point charge. When I look at any point on the surface of my Gaussian surface, we have electric field lines that are pointing outward along the radial direction. And every one of those field lines is parallel to the infinitesimal surface area that it passes through. So now is where we should start getting a little excited about how Gauss's law is going to work, because when we write out the first step of Gauss's law, Q enclosed equals epsilon naught E dot dA, well, we're expecting the same electric field magnitude at every single point on the surface of our Gaussian surface. And so I get to bring that electric field expression outside of the integral after I take care of the dot product. A lot of people want to skip that dot product, but it's still important. Well, no matter where we look, our electric field and our surface area are once again running parallel to each other. That dot product is hiding a cosine relationship. Since we have an angle of 0 between our vectors, cosine of 0 evaluates to a 1. Now we've lost the dot product. Now we can bring our electric field out to the front. The enclosed charge, Gauss's law says there has to be an enclosed charge. Well, our Gaussian surface has enclosed the entire charge of the sphere. So we can just call this Q, where Q is the total charge of the sphere. And the last thing we have to do is we have to integrate about the surface of our container. Our Gaussian surface has a radius of little r. We already know that the surface of a sphere can be written as 4 pi r squared. We're done with the integration, so it's time to rearrange for E. But we get exactly what we got before. We get the point charge expression. Where R is outside of the physical radius of our conducting solid. Okay, well that kind of brings an interesting question. If little r has to be outside of the physical radius of our solid conductor, just how close can we get to that conducting sphere and still measure the electric field? Well, the only condition that Gauss's law has is that your surface container has to contain the charge. So if we wanted, we could actually take our charged sphere and we could bring that radius of little r closer. The question is, how close can you get and still enclose the charge? Well, physically, the closest that you could get would be right on the surface of that sphere. Maybe I can use the highlighter, get a better, yeah, that's a little bit better. So physically, the closest that I can get and still enclose all of the charge is to let R equal R. But from there, all of the math is exactly the same until we get to this point. Now we're talking about having a container that has a radius that is no longer larger than the radius of the charged sphere, but equal to. And so this charged sphere will still act like a point charge as long as we are outside of it. And the way that the math collapses for Gauss's law tells us that we can get as close as sitting on the surface of the sphere and still use this expression. So with that in mind, now we need to consider the other three types of charged spheres that we can have. We just considered the conducting solid. Let's take a moment and jump to case 3. In this case, we have a conducting shell. Okay, for a conducting shell, this means that everything else about the sphere is going to be hollow. So we have a very thin shell here where the charge can exist, but the shell is still made of a conducting material, and so the charge will still have to distribute itself uniformly about the surface. And that's the only major difference between the two pictures. As far as Gauss's law is concerned, is there any difference? And the answer is no. As far as Gauss's law is concerned, these are the exact same pictures, because we are enclosing a total amount of charge within a Gaussian surface. We still have that Gaussian surface here, and all of the math is going to come out to be exactly the same. As long as we are outside of the sphere, whether we're sitting right at the surface of the sphere or we're somewhere a little bit further out, this expression is going to give us the same outcome as what the solid conducting sphere gave us. And if you need another way to argue that, well, try the center of charge argument that we used before. If all of this charge has been uniformly distributed about the surface of the sphere, then we can use the argument of center of charge and treat that sphere like a particle. And that means we get to use the point charge expression as long as we're outside the sphere, or even if we're sitting right on the surface of that sphere. So we were actually able to skip right to the end for that one. Instead of going through and reproducing all the math, we can use the concepts in the physics to show us what the outcome should be. And so now we'll go ahead and I'm going to jump over to case 4, since we already have the picture of a shell here. If we go over to picture 4, we need an insulating shell with charge on it. So we'll have another shell here of radius big R. And we still want to have uniform charge distribution. That's going to be a little difficult to do with an insulating material, but we discussed this in a previous video. If we came in here and we polished the surface of this of this insulator with a dry rag that would actually physically move the charge around the surface of the insulator, and if we did that long enough, we would ultimately achieve a uniform distribution of charge. The only difference between the two is that once this charge is placed where it is, it cannot move. But that's okay, because we want the charge uniformly distributed. Once we achieve that, is there any difference in these two pictures? We both have thin shells of uniform charge distributed about their surfaces. That uniform charge distribution says that we can either treat this like a center of charge, in which the sphere would act like a point charge, or we can try surrounding it with a Gaussian surface and see what the math of Gauss's law tells us. But everything about Gauss's law says, well, you've got the same charge enclosed by the same size of sphere for your Gaussian surface. You're once again going to get something that acts like a point charge. And then if we switch this to an insulating solid, this is one picture that will look a little different. For the insulating solid, one thing about an insulating material that's kind of interesting is that if you can figure out a way to distribute the charge throughout the physical volume of this insulating material, then it has to stay there. It can't move. So I now have charge stuck inside this insulating material. It can't move, but somehow we've magically been able to produce uniform distribution of charge. So we've got a fixed amount of charge per unit volume everywhere inside this solid sphere. But because of the uniform charge distribution, as long as I'm outside the sphere, what's it going to act like? Well, the center of charge argument says it's going to act like a point charge. What does Gauss's law say? Well, if we put a Gaussian surface around this sphere, as long as we're outside the sphere or even sitting at the surface of the sphere, as long as we maintain that uniform charge distribution, it's going to act like a point charge. So all four of these case scenarios, well, it looks like it doesn't matter what we use, whether it's a solid or an insulator or a shell or whatever, as long as we have that uniform charge density. And I guess the answer is yes. It doesn't really matter. Every one of these case scenarios is going to have the sphere acting like a point charge, as long as we remain outside of the physical structure of the sphere. The reason I'm stressing so much how these four different scenarios can all end up with the same result is that we keep talking about remaining outside of the sphere. What we want to do next is we want to look at those four case scenarios. We had the solid conductor, we had the conducting shell, we had the insulating shell, and then we had the solid insulator. Of these four cases, what would happen if you wanted to measure the electric field at some point that was less than big R? So what would you do if you wanted to go inside of one of these spheres and measure the electric field? And we will answer that in the next video, because right now this video is getting a bit too long and we need a breather. But we'll come back for the next video and we'll explore what needs to be done in each of these cases to find the electric field inside of a charged object. We'll see you then.